person again. Share Dutta. Let me bring up your talk. Okay. So Ishir Dutta from MIT on exploring deposition observations as constrained on emissions. Thank you very much.
Sorry. Hi, everyone. It's nice to be here. My name is Ishir. I'm a third-year PhD student. Maybe folks on Zoom should not be staring at my neck. I'm a third-year PhD student working with Colette Heald at MIT. And I'm very excited to talk to you today about the last year's worth of work in which we explore the use of deposition measurements in the US to constrain emissions as a potential novel constraint on emissions. Before I begin, I'd like to thank our funding sources at NOAA, as well as the lovely folks at the NADP and CASTNET who maintain the networks and take the observations that I'll be using in the talk today. And the focus of this talk, even though it says emissions, the focus of this talk will be inorganic aerosol over the US, which comprises about half of PM over the US. And as you know, in order to study the trends in these in inorganic aerosol, we think it's relevant to study the trends in emissions of precursor gases. And for those of you who did attend this session yesterday, you know how challenging it is to assemble any kind of emissions inventory. And it's extremely time and labor intensive. And typically emissions inventories are assembled for a single year, maybe back and forth, there might be a year plus or minus. And for example, the EPA releases its national emissions inventory, or NEI, about every 3 years. So the cartoon on the bottom left of my intro slide sort of gives you a sense for a working hypothesis, which is really quite simple. What goes up must come down. And this is especially true for species that are quite short-lived and are primarily physically removed. And luckily for us, secondary inorganics are both of these things, otherwise this talk will be quite short. And so this gives us some confidence in using this approach of long-term continuous deposition measurements to constrain emissions. Within this project, we chose GEOS-Chem, the GEOS-Chem model, as our translator between emissions and deposition. And just because we've chosen the GEOS-Chem model as the translator doesn't mean that it does a perfect job. So I'd like to talk to you about a few caveats that we considered while doing this work. So on the left-hand side, the first caveat, of course, is that all deposition measured in the US doesn't necessarily originate from emissions in the US. And so the map shows the sort of fraction of SOx deposition that comes from CONUS anthropogenic sources. And this sort of makes sense, right? There's a lot of SOx in the eastern US that primarily comes from, say, coal-fired power plants. And so the fraction is much, much higher in that region. And what that really tells us is that measurements made in this region, deposition measurements made in this region, are much more likely to better constrain the trends in anthropogenic emissions over the US. And we should also look out, in this work for the impact of both transboundary and natural sources, right? All deposition doesn't care whether it's anthropogenic or a natural source. The second caveat is sort of, as I alluded to earlier, that the model may or may not be doing a perfect job of translating emissions into deposition. And so it's sort of an assessment of model bias and representation of deposition. Here I've shown a sample year, the year 2013, showing a wet and dry deposition on the bottom and top scatter plots, respectively. The black line is the 1-1 line comparing the model and observations. And so the wet dep observations are taken from the NADP National Trends Network, and the dry deposition is taken from the CASTNET network. And as you can see, the model does a pretty good job of representing the annual site-wise deposition, both the magnitude and the fractionation of wet and dry, which is shown in the bar plots on the right-hand side showing dry and wet depth. Now that you have an overview of our proposed approach, we can put this all together and look at the relative trends of emission and deposition, which is shown on the plot on the left-hand side, to sort of orient you as to what's going on here. The red line is the EPA best estimate of SO2 emissions. This is from the EPA NEI National Tier 1 CAPS Trends Report, and is sort of assembled from stitching together multiple different NEIs, interpolation between NEIs, projection where interpolation is not possible, and is sort of, again, like I said, our best guess at SO2 trends over time. Second is the blue line, which is sulfate wet deposition measured at NADP sites. And as you can see, there's a decent agreement between the blue and red lines, but it's not a perfect agreement by any stretch of the imagination. And this is because wet deposition is only part of the story. We really have to look at total deposition. And luckily for us, the CASTNET network comes online in the year 2000. And so we can calculate total deposition, which is shown as a relative trend in the green line there, starting in the year 2000. And that really gives us quite an excellent agreement with the SO2 emissions in the red. Now, the black crosses there are the model years for which I've run the GEOS-Chem model for a full year. And so the black cross represents the relative trend in total model deposition, which again lines up quite well with the measured trend in deposition, sort of indicating to us that the measurements might be a good constraint on emissions. Just to sort of put a bow on things and wrap things up, we think in this work we've demonstrated, the challenge of assembling emissions inventories that may be assembled through disparate means, through disparate models over years. And we've proposed the use of consistent, spatially heterogeneous measurements made going back to the late 70s for wet deposition and then the 2000s for dry deposition to constrain these emissions and certainly give us a good sense of the trends over time. We've shown that the GEOS-Chem model is quite skilled at capturing SOx deposition accurately, both the magnitude and speciation over time. And it suggests that this approach might work well, at least for SOx. The longer version of this talk online, for those of you interested, does include a discussion about the NOx system, which of course is a bit more complicated. There are more natural sources, there are more reservoir species to consider, and that will form some of the basis for our ongoing and future work, which will also expand to a consideration of reduced nitrogen, so the NHX system, which is even more complicated. But I look forward to sharing those results with you at a future session. We'd like to, obviously disaggregate a little bit more about, I've alluded to in this talk about the spatial heterogeneity and the changes over time. And so that'll form the basis of my work going forward. Thank you very much for your time. I look forward to taking your questions at the end of the session. And of course, feel free to email me if you're online.
Thank you, Ishir. So the last, Ishir, what fraction of sulfur emitted in the US is deposited over the US?
Yeah.
Does that limit what you can learn from deposition?
Yeah. So
can you use the microphone?
Yes,
so
I don't know. Does that work? All right, cool. Yeah, that's a really good question. Given that much of the high volume sources are in the eastern US, we do expect a good amount of loss over the Atlantic of Canada. But my estimates are around 68 to 69%, but that is also subject to change based on what kind of wet deposition scheme we're using in the model, which is currently under revision. So I would say anywhere between 68 and like 75% is reasonable to say.
Okay, thanks. The question for the people online.
Sure. So I think what is being asked is why the wet dep trend diverges from the emissions trend, and whether it may be because of an influence of the background emissions, or whether natural or transboundary. And I think the right, well, I don't want to be too confident, but I think the right answer is that, again, I think this has to do with the national trend versus the regionally relevant trends that better capture a larger fraction. So yes, I think there is a significant influence in the background. So to give you a sense of, say, the SOx system, in regions, say on the West Coast, where there's very little SO2 emission, the decadal decline is about 23% per decade. And in the Eastern US, the decadal decline in wet dep is about is about 35% per decade, which much more closely matches SO2 emissions. So that would suggest that your hypothesis is in fact correct. The background is playing a large role. But in my plots, again, I've shown only the national trend. And the fact that total deposition matches quite well nationally, maybe, leads me to believe that I think before I say that with confidence, it's worth looking at regional trends based on my sort of fraction map. But yes and maybe no.
Thank you. Can you speak up a little bit?
Sorry, I didn't catch the last bit. Oh, okay. So I was showing that maybe I should have been a little bit clearer. I was showing relative trends rather than absolutes. So the units are not in kilograms of sulfur per hectare. They're in like relative scale to the year in which you start.